Okay, so in this video, I'm going to be using the convolution theorem to solve an inverse Laplace transform of a slightly more complex form. So let's go straight in. So we've got the inverse Laplace transform of s on s squared plus 1 all squared. So normally what we could do is just use the method of partial fractions and then separate those variables and then find the inverse transform that way by exploiting the principle of linearity. But what we're going to do here, we're going to use the theory of convolution. So first of all, just to recap, we said that and it's always good to do this because number one, it reinforces your memory of the subject, and also it's good for justifying your answers. If anyone wants to say, well, justify why you're doing whatever, it's a good way to do it. So we can say that the Laplace transform of f of t dot the Laplace transform of g of t is equal to the Laplace transform of the convolution of f of t and g of t. So therefore, if we take the inverse Laplace transform of the Laplace transform of f of t dot the Laplace transform of g of t, that must equal the inverse Laplace transform of the Laplace transform of f of t dot g of t. And of course, the inverse Laplace transform of the Laplace transform cancels Laplacian operation, meaning that we're left with the product of, that's terrible what I did there, that's a sin. f of t convoluted with g of t, not dot t. So we can also say that the abbreviation or the syntax that we use for the Laplace transform of f of t is capital F of s, dot the Laplace transform of g of t is going to be capital G of s, and that's going to be identical to the inverse Laplace transform of the Laplace transform of f of t convoluted with g of t, i.e. the convolution of f of t and g of t. So we can just write that as f of t convoluted with g of t. So, in other words, whenever we have two products that we don't know what the inverse Laplace transform is, we can use the principle that the inverse Laplace transform of the product of those two individual components are going to be equal to the convolution of the inverse of each individual component. So let's go ahead and have a look and see what we have over here. So we've got the inverse Laplace transform of s on s squared plus 1 squared dot product with 1 on s squared plus 1 squared. Is that correct? Yes, it is, because it's s squared plus 1 all squared, and that is squared with that. So, as you can see very clearly from here, what we can do, we can use these two things as the products. And if we find the inverse transform of this product and the inverse transform of that product, and we convolute those two transforms together, inverse transforms together, then we should end up with the inverse transform of the dot product of these two products. So, let's go ahead and do that and say f of s will be s on s squared plus 1 squared, and we can say that g of s is going to be equal to 1 on s squared plus 1 squared, and that implies that f of t is going to equal cosine t, and that implies that g of t is going to equal sine t. I'm a little bit tired, so I might make a few mistakes. I do apologize if that happens. So let's see what to do. Right, so therefore we can say that if we convolute cosine t and sine t, we should get the inverse Laplace transform of s on s squared plus 1 squared dot 1 on s squared plus 1 squared, which is the question. So we can say that the convolution function is going to be, let's just have the definition between infinity and minus infinity, that's going to be a tau, of f of tau dot g of minus tau plus t d tau. We also have to bear in mind that what are the actual limits, so that we know that that Laplace is defined right from the very beginning of the semi-infinite integral of f of t e to the minus s dt. So therefore, we know that the lower limit must be 0, and the maximum limit, the highest limit. Well, let's think about this. If we reflect g of tau in the y-axis, we're going to end up with g of minus tau, and then we add t. And we keep adding t, so we sweep the two functions, and then we get the product for all values of t, of the magnitude of the area of overlap, which is the definition of the convolution function. Now, what is the maximum value that tau can actually take? So remember, in Laplace, if we have anything to the left of t equals 0, the magnitude is going to be 0 in this entire region, okay? Because the definition of Laplace is between positive infinity and 0. So, if we want to describe where the domain is, we can say that's going to be t minus tau. And t minus tau has to be greater than 0, which means that t has to be greater than tau, which means tau must be less than t, meaning that the maximum value of tau that tau can take is t. Why? Because if tau goes beyond t, then we can see that g of the argument is going to be negative. And if we're in a negative domain, then the function will be 0 from the definition of Laplace. And that's why tau, that's why the maximum limit when we do the convolution of two functions in working out inverse Laplace transforms, the maximum limit that tau can take must be tau. Because if tau is greater than t, then the domain, the argument, is going to be less than 0. If the argument is less than 0, the function is 0. So the maximum value is t. So let's go and rewrite the integral function for the convolution, which will be tau equals 0 to tau equals t of f of tau, which we're going to call cosine tau. And that's going to be dot product with g of minus tau. G of minus tau is going to be sine minus tau plus t d tau. So now we have the convolution function that should give us f of t convolved with g of t to form the inverse Laplace transform of f of s dot g of s, i.e. s on s squared plus 1 all squared. So let's have a go and try and solve this integral. So the first thing to note is that sine t minus tau should register a trig identity of sine a plus b is identical to sine a cos b plus cos a sine b. Okay? So therefore we can say that sine t minus tau must be equal to sine t cosine tau. Forget that just for the second. What we'll do, we'll say sine a minus b is identical to sine a cosine b minus cosine a sine b. So we can therefore say that sine t minus tau equals sine t cosine tau minus cosine t sine tau. Let's substitute this back into the integral. So now we have the form of the integral. I'm just going to refocus the camera because I think there's a little bit of a focus alignment. Okay, so now we have the integral of the convolution function between tau equals 0 and tau equals t of cosine tau sine t cosine tau minus cosine t sine tau d tau. Next, let's expand the brackets. So we now have the convolution function between t and 0, remember that's tau, 0 to t, of cosine squared tau sine t minus cosine t sine tau cosine tau d tau. And remember that the dummy variable tau, in terms of d tau, means that the t terms are constants, which means we can take them out. And we have the principle of linearity with integration so that we can take the integral of this and subtract the integral of that. So let's go ahead and do that and take out whatever we can. Okay, so we now have the convolution function as sine t times the integral of cosine squared tau, d tau, minus cosine t times the integral of sine tau cosine tau d tau. So the first thing to notice is we've got some identities going on here. So we know that cosine 2 theta equals 2 cosine squared theta minus 1, I think. Well, blinking well, I hope so. So we can therefore say that cosine 2 theta plus 1, all on 2, equals cosine squared theta. So we can therefore say that cosine squared tau equals half of cosine 2 tau cosine 2 tau plus 1. So that should get us going over here. And over here, we've got the famous sine 2 theta identity, which equals 2 sine theta cosine theta. Sine 2 theta equals 2 cosine theta, 2 sine theta cosine theta. So therefore we can say that sine tau cosine tau is identical to half sine 2 tau. And that should get us going over here. And then we have now the convolution function in this form, which should be fairly easy to integrate. So we're just going to go ahead and do that now. Paper up. So we can now say that the convolution function is going to be sine t dot a half of 1/2 sine 2 tau plus tau. It's always important to be very, very careful when doing this, because this is usually a good area that goes wrong if you're not really concentrating. And then we have cosine t dot a half, integrating sine 2 tau, so that's going to be minus a half cosine 2 tau, and that's going to be evaluated between t and 0, and here this is going to be evaluated from t and 0 again. So let's just expand these brackets. And what we can do to simplify this, we can take out the quarters, because there's lots of quarters here. Now, when we get to this stage, it can look a little bit intimidating. What I do is look for the trig identities that are most immalleable, the ones that really only have one. So things like cosine 2 theta, there's 3 identities that we have for those, for that one. Sine 2 theta, however, I'm only aware of 1. So let's go ahead and substitute that for sine 2 theta, and then we can choose something for cosine 2 theta to see if we can get that in a more friendly form. So let's do 1/4 sine t times sine 2t is 2 sine t cosine t plus 2t sine t plus cosine t cosine 2t minus cosine t. Now let's expand that and see what we end up with. Okay, so now we have 2 sine squared t cosine t plus 2t sine t plus cosine t cosine 2t minus cosine t. So initially, that looks a little bit scary. Let's have a play around with cosine 2t. We know that cosine 2t equals, in terms of trying to get things in terms of a sine format would be nice, 1 minus 2 sine squared t. So cosine t minus 1, 1 minus cosine 2t equals sine squared t, and that's divided by 2. So we can say that sine squared t is a half of 1 minus cosine 2t. So let's go ahead and substitute cosine 2t with 1 minus 2 sine squared t. So we can now see that the convolution function is 1/4 2 sine squared t cosine t plus 2t sine t plus 1 minus 2 sine squared t cosine t minus cosine t. So now that we have the convolution function in the form that we do now, we can start to see that the 2 sine squared t cosine t over here is going to be commensurate with the 1 minus 2 sine squared t cosine t over here. So let's expand that and rewrite the convolution function underneath, and hopefully we should start to see some of the terms cancel. And here we can see we've got the 2 sine squared t cosine t and the minus 2 sine squared cosine t. So those terms are going to cancel. The cosine t and the minus cosine t's are going to cancel, and we're left with 2t sine t on 4. So we can now state that the actual convolution function is going to be 1/4 dot 2t sine t, which is going to be 1/2 t dot sine t.